2 weeks ago, we hosted a American Nuclear Society topical meeting called Nuclear Emerging Technologies for Space Applications. And typically that conference, which is held every year, is around 200, maybe 225 people. We had it here in Idaho Falls a couple of weeks ago. It brought in 400 people. And we had people here from a total of 9 different countries, 3 different continents. You've got everybody from like Dubai launching a mission to Mars. You've got people from India launching things to go to Mars, Russia. It's just exciting. It's a good time to be in the field of power systems for NASA applications.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America.
That is willing to
We're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation
We need scientists to design new fuels.
and focus on net public benefit
We need engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those
then
technologies.
we will march towards this.
We need workers to operate assembly lines that hum with high-tech,
We
zero-carbon
have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Okay, welcome to another episode of the Fire to Fission podcast, where we talk about energy-dense fuels and how they can better human lives. We're joined today by Stephen Johnson, the Director of Space Nuclear Power and Isotope Technologies Division at the Space Nuclear Power National Technical Director. No, I think I messed that up. It's kind of a long title, but at Idaho National Labs. So, Stephen, how you doing today?
I'm fantastic. Yourself?
Excellent. Super excited to dive into this conversation and hear about what you guys are doing with space and nuclear in space. But before we get to that, let's hear a little bit about you. Why don't you give us kind of a brief introduction about yourself, and let's dive into some of your background.
Yes, I've been at the lab here a little bit over 31 years. I have a PhD in chemistry from Iowa State in Ames, Iowa. Did a year or so at Los Alamos National Laboratory, then joined the staff here at Idaho National Laboratory West, which was then turned into the Idaho National Laboratory. I've been doing things in space nuclear power since 2002.
Wow. Have you seen it change a bunch since then?
Oh, I don't know whether the change is external or internal. A little bit of both, I imagine. But it's been an exciting last 20 years. There seems to be a fair number of missions on the NASA side that want and need to be enabled by nuclear power. And things were much more exciting early on, where we had to move a program from the Midwest to out West and do it in very, very short time, build a building, hire 70 people, and get a product down to Kennedy Space Center for launch. Those were very exciting times. I'm kind of glad that kind of excitement and schedule pressures a little bit behind us now, and things are much more regular, but still interesting. Our last launch was the 2020 Perseverance rover. I don't know if you've ever been down to Cocoa Beach, but when you get down there in early April of 2020, after the Governor DeSantis had shut down Florida, and there's nobody on the highway, nobody in Cocoa Beach. There's a guy with a clicker to get into, be one of the 200 people going into the Walmart store with everyone wearing masks and little arrows on the highway saying go this way or go that way, but don't go against the stream. So that was a unique experience. I hope it's never repeated.
Absolutely. Me too. Before you got into space or at INL, what were you doing? How'd you come upon it?
Yeah, so I was running the electron microscopy lab here, and I had a high-level wasteform characterization group. We did some testing with wasteforms using plutonium-238 as a dopant, and that was the heat source material that's used with the radioisotope thermoelectric generators for NASA. So when DOE came calling, I was picked as the person to write the proposal, which was way outside my field, really. But I'm a trooper, so I put stuff together, had a really good engineering partner, and managed to write a proposal for $15 million in about 2 weeks and got the project moving in here. And then I had time to learn about 9 months of interstate trucking to get 28 tractor trailer loads of equipment from Ohio to here, design a building, and then in the subsequent 6 to 9 months after designing it, getting it built. There's nothing like pouring concrete the end of January in Idaho when it's 6 degrees outside. It just makes you feel good.
Gotcha. Okay, and this division is in Idaho, obviously. You just said that.
Yeah, the Idaho National Lab right now is about 5,700 people. We have several campuses kind of stretched out over 890 square miles in the eastern Idaho desert. And we employ 50 to 70 people, bring in anywhere from $20 to $50 million a year of business volume.
Paying that, or what kind of business or revenue are you guys bringing in?
Yeah, so right now NASA picks up the full bill. So so they're paying everything, and it's an interesting way to go. And we are one of 3 laboratories on the DOE side that support this program. Oak Ridge National Laboratory supports it, and Los Alamos National Laboratory in New Mexico supports it.
Got it. Okay, so tell us a little bit about the program. Why nuclear in space?
Okay, so nuclear is used as a can't do it any other way, or something where it enhances the mission a great deal. For example, if you're going to the dark side of the moon, solar power and batteries probably aren't going to do it for you. If you want to go to the far reaches of space where solar panels would have to be so large that you couldn't envision in deploying them. For example, 1977, August and September, Voyager 2 and Voyager 1 were launched. They were to go through and tour our solar system, all the planets, send back images. They needed a power system that would work when they were very far from the sun. Radioisotope power systems, where they were powered with something that had a half-life of a radioisotope of about 88 years. So those probes were launched not quite 50 years ago, but more than 45 years ago. They're still working. They, in 2013 and 15, they passed that little spot on the edge of our solar system, which said, last stop for food and drinks, next solar system, X light years away. And so they are now out in interstellar space. And the power systems are still functioning. That's the thing that's really kind of neat. Those 2 probes are out there. Pioneer 10 and 11 are out there, and the New Horizons Pluto. We did the power system for the New Horizons Pluto, and that was launched in 2006. Those are the type of missions where you can't pull them off any other way, or you want something to operate on Mars and operate all the time. Radioisotope powered, nuclear energy powered is the way to go. You get a good return on your investment, and it keeps going for a long time.
Do you know the expected lifespan of the Voyager systems?
Here, this will probably make you laugh. They were launched in 77, and the answer was 5 years.
So under promise, over deliver, right?
Yeah, either we're really bad at counting, or we under promise and over deliver. That's been the hallmark for the radioisotope power systems. Currently, we shoot for about a 17-year certified lifetime, 3 years of storage, and a 14-year mission. And so Voyager is always our poster child. The Cassini probe that was launched in 77, and it orbited Saturn, the planet Saturn. And that was it had done everything it intended to do by 2017. So they then diverted it into the planet, and it burned up on the way down. But I mean, with Mars, we've got 2 current rovers up there working. One was launched in November of 2011. That was Curiosity. The other one was launched July of 2020. That was Perseverance. That's the one with the helicopter, that Ingenuity that people get to see. They're both working. So the power system for Curiosity was actually fielded in 2008. So it's approaching that magic 17-year certified lifetime, but it's still getting data. And so that's the exciting thing. You get a good long payoff for your investment.
Got it. Yeah, I mean, the solar flux, just from as you move away from the sphere, from the point solar source, it's a cubic function for how fast your power drops off, right? So, like, because Mars is further away, I think I read recently solar reduction, or the solar flux is reduced by like 50-60%. And so the size of the solar panels you'd have just would be enormous.
Exactly.
Yeah. Okay, so you guys are focused on the power systems for these satellites, these exploration rovers. Is there any, well, let me ask, what is the power system that's typically used? Is it like a Stirling engine, or you just got a little micronuclear reactor on board?
It's a heat source made out of plutonium-238, so about an 88-year half-life. That puts off a fair bit of heat. That's kind of the inner core of the radioisotope thermal electric generator. And you surround that with thermal electrics that are electrically connected. So you make a hot side and a cold side, and you set up kind of a small electron pump based on your delta T between inside and outside. And you hook all that stuff together, and you end up having a passive, no moving part thermoelectric generator. Now, your conversion efficiency is 5 to 7%, not the highest, but there's no moving parts. There's nothing to break. There are different power systems, different converter systems that are under development. You mentioned one, a Stirling engine, where you have a movable piston and you're working on a working fluid of gas of some sort. And the advantage of that is you can get 20-25% conversion efficiency, much better than 5 to 7. The downside is you've got moving parts. So if something goes wrong, once it's up there, it's up there. There's no repairman that's going to make a road trip there.
Moving parts leads to failure much faster. So thermoelectric generator, I mean, there's not like a battery pack on board that this is charging, or
there are on several of them. You're absolutely right. On Perseverance and on Curiosity, there are battery packs, and the radioisotope power system is essentially a battery charger. Now, on the unit that's intended to go to Titan, which is a moon of Neptune, actually of Saturn, sorry. There, they are going to use the power system directly. And that's kind of an interesting thing. It's actually going to be something, closer in size to a small car, and it'll be a quadcopter. And speaking to the principal investigator at one point, Dr. Z.B. Turtle from the Applied Physics Lab, Johns Hopkins, Columbia, Maryland, the gravity on Titan is very low, and the density of the atmosphere is very high. So to put it in layman's terms, if you could have a human being there survive the cold and flap your arms, you could fly. So, but that'll be more of a direct use of the heat and the electrical power from the RTG. We're actually working on a slightly customized RTG right now for that mission. And the latest launch date that I have from them is a 2027 launch date.
Okay. That's fascinating. I mean, there's so many different types of systems that are advanced and they're not typically used on Earth. Well, that's a great question. Why don't we typically use these systems terrestrially?
Yeah, so there are some that are used terrestrial. Usually they're powered by strontium-90, which is an isotope with about a 29-year half-life. We've had several of those. They're used for things like, let's say, weather buoys, maybe things that you want to put somewhere and only make one trip there, like Antarctica would be a possibility. Another country in the world that had several of those was Russia. They put over 1,000 on their northern shoreline, as surveillance systems. Then they kind of forgot about them, which is the downside. But they had over 1,000 of those deployed along the northern coast of Russia. And I believe they've collected most of those because people thought they were really neat if they ran across them because, they're warm and it's great. The bad part is when you get radiation poisoning, not so good. But use them as in-home heaters. Yeah, so typically strontium-90, the reason for that is it does give off a good amount of heat. It also gives off some radiation that takes lead shielding to make them safe to be around. And weight costs a great deal to get up in the space. So you want something that's as light as possible for space use. Hence plutonium-238 for that.
Got it. But you don't necessarily have to use uranium or fissioning atoms or heavy elements to create the heat, right? I mean, on these thermoelectric generators, I just looked up a picture of one. It's essentially just a solid state metallic block that gets hot on one side and is cooler on the other side. And then when the heat fluxes, it generates a current. Am I thinking about that correctly, or is it
Yeah,
more complicated?
that's you've got the right model there. As far as uranium, the U.S. has flown one space reactor back in the mid 60s, the SNAP 10A. The Soviet Union at the time flew, I'm going to say somewhere in the 30, 35 different satellites that had small space reactors on them. And that's where you are doing a fission reaction that is producing energy, producing heat, and then you use a similar type of converter to take that heat and turn it into usable electrical power. The U.S. is working on a couple different reactor technologies. One would be for, say, a base on the moon or Mars where it would concentrate on taking that thermal energy that's created by the fissioning act and turning it into electrical power where you need, say, tens of kilowatts of electrical power. Another one would be nuclear thermal propulsion, where you're using the reactor essentially to provide you with a stream of hot hydrogen. Hot hydrogen's ejected one way, your rocket ship goes in the other way. That would be a way that we could get, say, human beings to Mars and back in a reasonable amount of time. We can get things there now using chemical rockets. We just can't get them back.
Yeah, it's a one-way ticket.
Yep.
Okay, I mean, we've kind of bounced around a little bit from our pre-scripted list of questions, so I'm fascinated by the topic. But you covered it a little bit with some of the advances that have, I guess, we've progressed from kind of the Voyager to the spacecraft that's going to Titan. But let's just dive in a little bit more. I mean, in my mind, I see Stirling engines for like commercial energy reactors. We see them hooked up to a power system like a turbine or reciprocating engines all the time, but we don't necessarily use those systems for space.
Yeah, I think Stirling's, if it's for a shorter length of time than, say, the 17 years I mentioned earlier, and if they're where they can be serviced, excellent choice. But if it's where they can't be serviced, and let's say if you're going to Titan and you take 4 to 6 years to get to Titan before you even start doing the fun stuff, all of a sudden reliability is your number one thing that you're concerned about.
Yeah. That makes sense. Do we have a lot of satellites and other space objects that are nuclear powered?
The U.S. has launched, I forget whether the number is 27 or 28 over the years, but it's in that ballpark. And some of them had more than one power system on there. So it's 27, 28 missions and probably approaching a little bit shy of 50 power systems up there.
Okay, cool. I mean, you mentioned that, we use plutonium as one of the fuel sources, and people are paranoid about plutonium and proliferation concerns. Are there any safety or security concerns? I mean, one of the disposal or waste handling methods that has been proposed is, well, if we can't put it anywhere, let's just launch it into the sun. People then get freaked out about, well, what if it blows up when it launches? Is that still a concern with these size systems, or is the source just so much smaller that it's less of an issue?
We do an extensive launch safety package for every mission that goes up. We look at it several different ways. We do public outreach in that regard. I won't say the probability is zero. The probability is very low. And we try to engineer in to the heat source a good probability that even if you had an accident, you're not going to be spreading material around. It's very robust. It is extensively tested at typical what I call a skydiver velocities, which is the speed that it would come back into the earth, about 120 miles an hour, something in that range. And so it's something that we plan for, it's something that we model, it's something that we test to, so we can say, hey, this is a safe system. And so that's how we address that.
Got it. I mean, in my mind, there's just so little fuel, and maybe I'm conceptualizing it wrong. How much of the payload is actually the fuel for most of these systems?
In terms of the plutonium fuel or in terms of the chemical rocket fuel?
The nuclear fuel. I mean, the chemical rocket fuel I get, then
the current power system, which is a multi-mission radioisotope thermoelectric generator, MMRTG for short, has approximately 10 pounds of plutonium oxide on it. Okay. And so that is a very, very small percentage of the total cargo. I would say much under 1% for the most part.
Versus if we had to use the same amount of hydrogen, it would be thousands of times more.
It's little apples and oranges there, but plutonium is a good concentrated heat source. And again, the scientists and engineers are very clever in terms of exactly how little electrical power they need, because they've got to manage all that on a daily basis.
Right. Okay, so you mentioned Mars once, but can we chat a little bit about NASA's Mars Scientific Laboratory mission?
Certainly. MSL took off, was launched the Saturday after Thanksgiving in 2011 and arrived at Mars approximately, 8 months later, because it came in our time zone. It was about 11 o'clock on August 5th of 2012. And it was exciting. They had 2 satellites on Mars so that they could time it so that when it was coming down in and screaming down at supersonic speeds and deploying a parachute, and finally a sky crane to lower it down the last bit, they had 2 satellites that were observing it, which was pretty cool, actually. And for my team here, we were all back here in Idaho Falls. So we actually rented out a establishment at one of the hotels and took over the live screen and had the NASA channel on, and it was exciting. And then the next day was Monday, and I was at the front gate along with others handing out about 800 Mars candy bars. So, when you only have a party every few years, you try to do the best you can. Hey. So
that's super cool. And your guys' power system is on that spacecraft, right?
Yeah. So we also, you can work your entire life on certain neat projects, but you never get an opportunity like to have a Hot Wheels car. This is a Mars rover or a Lego set. So
they made replicas. For folks that are just listening, Stephen just held up a Hot Wheels toy car and then an actual Lego set of the systems that was built, right?
Yeah, the Lego set I should have bought a lot of. They were going for $50. And if you have an unopened one like I do, they're now $400 to $700. So, like I said, you can work your entire life and never have a project with toys, So, hey, you got to be excited.
Yeah, that's awesome. Would you say interest in nuclear technologies for space applications is increasing now?
I think so. Just 2 weeks ago, we hosted a American Nuclear Society topical meeting called Nuclear Emerging Technologies for Space Applications. And typically that conference, which is held every year, is around 200, maybe 225 people. Last year in Cleveland, it was 379 people, all-time attendance. We had it here in Idaho Falls a couple of weeks ago, it brought in 400 people. And we had people here from a total of 9 different countries, 3 different continents. You've got everybody from like Dubai launching a mission to Mars. You've got people from India launching things to go to Mars, Russia. It's just exciting. It's a good time to be in the field of power systems for NASA applications.
Absolutely. Is there more interest from the private sector?
Right now, there's a great deal of interest from the private sector. Everybody's interested in going to the moon. They're interested in commercial flights going to the moon, which would be under the administration of the FAA in the United States. And they're interested in power systems. So they're looking at lots of different radioisotopes, lots of different power systems. And as well as the US Space Force is interested in that as well for small satellites. So all these things are going on. Everybody's scrambling for new technologies, whether it's a reactor or a radioisotope power system. It's an exciting time to be in the business.
Absolutely. We chatted with Atomo Space a couple weeks ago and hope to have them on the podcast too. And they're doing some pretty cool stuff with space vehicles or tow vehicles, radioisotope propulsion. So we've seen a little bit of it. So what other uses of nuclear technology do you foresee in promoting space exploration? I mean, we covered a lot of them, but
I think we covered most of the ones that I see. There's always small amounts of other radioisotopes, Walt-60 or various neutron emitters that are used as a portion of an analytical instrument in order to get additional analysis capability. Those are along even on solar missions. The big ones, radioisotope power and nuclear reactor fission power, are the large ones that really make a huge difference in the success of a mission, and once you get up there, how much data you can get and how fast.
got it. We talk a lot about propulsion systems and accelerating, and how can you travel or have interstellar travel, but not a lot of people talk about decelerating or slowing down. I mean, some of the systems that got to Mars, we haven't used any for strict propulsion purposes, have we?
No, not at this time.
Yeah. Is there any plan or roadmap for that?
There's certainly a plan. I think nuclear thermal propulsion, which uses the stream of hot hydrogen, is something that is in the works for maybe about 15 to 20 years from now. With fission surface power, that's something they would like to send to the moon for a demo, by the end of this decade. There's a military DoD funded effort under DARPA, and they're hoping to get something that's in a Earth orbit as soon as 2027 and demonstrate it there. It wouldn't be capable of going to Mars, but it would be a demonstration of a reactor in a Earth orbit situation. And they're looking, that's only 4 years away. So
cool. That's awesome. What are some of the biggest challenges that you see with nuclear and space in the future?
it's always challenging getting enough people in the door here in the States to staff things. It is challenging depending on what isotope you're using to obtain that isotope. It was much easier when we were involved in the Cold War because then people were out there making lots of different isotopes for military purposes. And so NASA could kind of piggyback on that effort. Now it's more of a standalone type effort. And you can make some of those things with the current research reactors in the US, but those are kind of few and far between. So it's the technology's not unknown. We know how to do things. We know how to separate things from a chemistry point of view. It's just finding enough time in reactors to make the isotopes that you want. That can be a challenge.
Interesting. Yeah, I mean, if we're creating, literally performing alchemy and creating elements from radioactive decay, then yeah, you got to have a system that does that, right? And
yes,
those systems aren't infinite. So do you guys engage with the NRC at all?
No, DOE is its own regulatory capability. And so we're on that side. With the most current setup that was developed over the last 4 years, you basically have 3 authorities. NRC is pretty much strictly commercial nuclear plants. DOE is on the DOE side, and the FAA was set up to do commercial type things that fly. But those are the 3 agencies that are involved in the U.S.
Okay. Well, Stephen, this has been great. Just a couple more questions for you. So, how can people help if they want to get involved, or if they want to be part of it, or if there's anything that they can do to just be cheerleaders for you guys? How can people support you?
We're always looking for people to help do outreach. That's something that a lot of my staff does, whether it's at the school level, elementary school. We do anything from there to Rotary clubs, any type of club that people are interested in. I don't think we've ever turned down a request. I've had some odd ones where you go out to a school and they didn't really tell you what age group at the school, and you get there, it's a consolidated school district, so you have first graders through 12th. And I mean, what do you do? But I remember somebody repeatedly asking me, well, hey, yeah, so where do the astronauts go? And I kept on saying it's an unmanned mission. And they kept on coming back.
There's no people. They're like,
yeah, and finally I was like, hey, I said, they just missed the launch. They were late. We had to leave them behind. And so that's good. And if they're interested in really being involved, I mean, take the STEM courses, take the science and technology, engineering, math. I have all sorts of people, engineers, technicians, quality assurance people that are part of it. And there's no perfect background to be it, but there's plenty of opportunities out there, both at the Idaho National Lab, other national labs, NASA, places like the Jet Propulsion Lab. And there's a lot of times when things are fairly ordinary in between missions, but then you get a mission and it's the greatest group dynamic you ever see. You get down there and you're one of like 12 groups. There may be 1,000 people focusing on the mundane question of making the pointy end go up. I mean, and that's what it comes down to. And so it's always exciting at that part. And usually when we're down in Florida, which we are for 4 to 6 months, you get to see lots of Falcon 9s go up or other missions, and that's exciting too. So
yeah, that's awesome. Okay, Stephen, this has been great. Why don't you leave us with kind of your most positive vision of the future? What's the world going to be like in, say, in 20 years, and how is nuclear and space going to be involved in that?
Well, let's say if you go out 20 years, I hope that we're going to be talking about manned missions to Mars and perhaps a colony on Mars. I think that would be way cool. And a halfway colony, or less than halfway, a sustainable city on the moon, I think would be a good thing to be going on in 20 years' time. Hopefully I'll live that long. We'll see.
I bet you will. So, that's great. All right, Stephen, thanks so much. Appreciate it.
Thanks. You have a good day.